Check out this fractal. It's created by a weird number system. If we change the system, we get a new fractal, such as this one or this one. It's like binary, which uses base 2 and the digits 0 and 1. On the number line, we have 0 and then 1, but that's all the digits. We're using base 2, so we write 2 as 1, 0. Then 3 is 1, 1, and then we have But what if we switch the base to the imaginary number I, which squares to -1? The imaginary number line goes up and down. So I is here. Wait, I am here? Is that? It doesn't matter. We'll write I as 1, 0, because it's the base. So then 1, 1 has a 1's place and an i's place, so it's I plus 1, which is right here. Now, what about It has zeros in these places, then there's a 1 in the I squared place. So this is I squared. That's -1. So it'll go, wait, that's going to cause a problem with It has a 1 and an I squared. If we add those together, we get 0. Equals 0. And so does Base I is not good. It has a lot of duplication. Instead, we can use base I minus 1, which is right here. It's the new 1, 0. And then here is 1, 1, and then then we can add in the 5-digit numbers, and the 6-digit numbers, and the, oh, wait a sec, we gotta do the logo. Okay, then we can add in the 7-digit numbers and the 8-digit numbers. It makes this swirly fractal called the twin dragon. And I minus 1 isn't the only cool base. Check out I minus 2 and I minus 3. We keep getting squares because we're using imaginary numbers. But we could replace I with omega, which squares to -1 minus itself. With these imaginary numbers, we get a hexagonal grid, which means we can make hexagonal fractals, which I like to call... Wait, before we go any further, I'd like to introduce the person who began these explorations, Thomas Kaldahl.
Hello.
Could you talk us through how you got started with these patterns?
Yeah, so I saw how well base I minus 1 works for the imaginary numbers, so I wanted to see if I could get something working for the Eisenstein Integers.
Imaginary.
Right. So I found this pattern using base omega minus 1.
Yeah.
And the digits 0, 1, and 2.
What?
The digits 0, 1,
Oh,
and...
yeah, I heard you. I was just being a hype man.
Hype man?
Like in a rap song?
Okay. So this system works, but it's really scattered.
Scattered.
Some of the small numbers require a lot of digits.
Inefficient.
So then I took inspiration from balanced ternary and tried using digits 0, 1, and -1.
Fancy.
But that was worse because we can't even write 2.
Uh-oh.
I played around with the digits until I found 0, 1, and omega plus 1. And turns out they can actually represent every imaginary number. And they make this nice shape.
Fudge flake.
Wait, what?
That shape is called the fudge flake.
Why fudge?
Don't ask me.
Wait, that's the real name?
Yeah.
Sorry, I thought you pulled it from your imagination.
I wish. Well, thank you for that introduction.
Of course.
So now, after seeing some of these systems, we have a few questions. Why do imaginary bases create fractals? How can we construct other fractal systems? And what was the third question supposed to be? Let's start at the top. In binary, we have these single-digit numbers. To make the double digits, we slap a 0 on the end of them, and then each one gives birth to 2 new numbers, one for each end digit. And then to make the triple-digit numbers, we just do it again. Slap a 0 on the end, and each one gives birth. We can generate all binary numbers by repeating this process. Slap a 0, give birth. Slap a 0, give... Wait, the whole point is the imaginary bases. So let's try this process with base I minus 1. We start with our single digits and then slap a 0, give birth. slap a 0, give birth, slap a 0, give birth. Notice, each time we slap a 0, the shape spins and grows. If we take some number and slap a 0 on the end, that's the same as multiplying it by the base. And here's the key. I've been looking everywhere for that. Finally, I can get back inside. Okay, here's the important idea. Imaginary multiplication corresponds to rotating and scaling. When we multiply by the base, I minus 1, we're rotating by 135 tiny circles and scaling by root 2. That's why slapping a 0 makes the shape spin and grow. And this spinning, I should mention, imaginary multiplication also corresponds to rotating and scaling. Omega minus 1 rotates by 150 tiny circles and scales by root 3. In base omega minus 1, these digits make a triangle. When we slap a 0, we're multiplying by the base, so the triangle spins and grows. And this spinning and growing is uniform, so it's still a triangle, just spread out.
Yeah!
And then the next step, giving birth, fills in the gaps.
Convenient.
And notice, each color is now its own triangle. After a hex gets slapped with a 0, it gives birth, making a new copy for each end digit. This birthing process turns every single hex into a triangle. So as we continue the slap birth procedure, the shape gets broken down into smaller and smaller triangles while retaining the same overall triangle shape. And that's why it creates a fractal. So now we've answered this first question, let's move on to the third. I still don't remember. How about the second one? How can we construct other fractal systems? Let's try using base omega minus 2. We'll start with the same triangle, then slap a 0, give birth, slap a 0, give birth, slap a 0, give birth. The hexes are spread out. There's a lot of empty space between them because the birth rate is too low. With the previous base, omega minus 1, multiplication corresponds to rotating 150. Wait, that's not relevant. Don't look at that. And scaling by root 3. This means that the width scales by root 3 and the height scales by root 3. So the total area scales by root 3 squared, which is 3. That's why we use 3 digits.
What?
So that the birth rate matches the scaling factor.
Synchronization.
Now, with base omega minus 2, we're rotating by an irrelevant value and scaling by root Sven, meaning that we need Sven digits so that the birth rate will match. Hey, that's actually quite nice. We can arrange Sven digits to make a big hexagon. Let's watch as it slaps and births and slaps and births and slaps and births to make a new fractal. Now let's do omega minus 3. It scales by root 13, meaning that we need 13 digits, which is also really nice. We can arrange them to make a spiky hexagon, which slap births a new satisfying pattern. So that answers our second question. To construct a fractal number system, we pick some base, find its scaling factor, then square that to get the number of digits. If we use 2 omega minus 2, the scaling factor is root 12. So we need 12 digits. We can take that spiky hexagon and remove the middle. Then slap birth it to make, something's wrong. There's a big hole in the middle of the shape. All of the wholly numbers are undefined. We have no way to write them. This set of digits has some problems. First, we removed the digit 0. Every number technically has infinite zeros in front of the other digits, because each place must be filled. If we get rid of 0, then we have to put different digits in all those places, and we end up with an infinite sum. We can't write any finite values. Every number is undefined. But there's an easy fix. We can just shift the digits so that 0 is included again. That fixes the infinity problem, but the fractal still has a big hole. And that's because these shapes overlap. Look, the red shape crosses over the lavendist shape. This number can be written as the single digit 2 omega or the double digit 1, 2, which is the base plus 2. This is a problem. We chose 12 digits to match the scaling factor squared. When these match, we get one representation per number. But 2 omega got greedy and took 2 representations. Which means that another number ends up with 0 representations.
Inequality.
So how do we fix this?
Equivalence classes.
Yeah, we could use the equivalence classes mod the base, but I don't want to explain that. So let's just use our eyes. No, not the imaginary unit, our eyes. I created this website that visualizes imaginary number systems. Here we can see that holy spiky hexagon. 2 omega had an overlap, so let's move it. There's an empty spot right here. But that causes an overlap with 3 plus 2 omega. Watch it while I make that move again. You can see an outlined hexagon slide below it. So it should also move, maybe to this empty space. And now we still have a hole. We can find any remaining overlaps by slightly shifting the base. Notice that negative omega has an overlap. I'll shift the base again so you can see. So let's move that digit to this hole in the middle. And now if we shift the base, there are no overlaps. This set of digits works as a number system. But the fractal isn't that cool. If we tweak the digits a little more, we end up with this shape, which makes a well-behaved system and a cool-looking fractal. I wonder if we can tweak those other bases. Let's take the hexagon and try moving things around. This set of digits also works, and it makes a weird tilted Sierpinski triangle. We can also visualize the imaginary numbers, but I'll leave that for you to explore on your own. Follow the link below to play around. To get started, click the die to randomize, or click the hearts to see some of my favorite systems. Thanks to my recent supporters for helping to make this website possible. And thanks to Thomas for this awesome idea. Follow the link below to see some of his other projects. Well, it's not the same link as the imaginary basis visualizer. There's probably going to be like 4 or 5 links in the description. I'm not sure, I haven't written the description yet. Usually I record.